As you can see, the supercell possesses a well-defined hook echo as denoted by the yellow arrow. At the tip of the hook, we see an area of strong outbound winds, but very little in the way of inbound winds. At first glance, you might overlook this signature given its asymmetric nature, but when we switch to storm relative velocity, we see a much clearer depiction of a TVS, with an area of strong inbounds adjacent to an area of strong outbounds. This makes sense. Let's say our inbound winds within this TVS have a velocity of 55 miles per hour moving toward the radar. With a storm motion of 55 miles per hour away from the radar, the resultant base velocity reading would be an erroneous 0 miles per hour, and our outbound velocities would be drastically overestimated. With storm motion factored out, we get a much more realistic depiction of the velocities within the couplet and a much clearer indication of a TVS. At the time of this radar image, an EF3 tornado was ongoing, which highlights the importance of using storm relative velocity rather than base velocity in tornadic situations. In addition, TVSs within QLCSs can sometimes be difficult to ascertain given their typically weak and brief nature. While this can be the case regardless of the velocity product used to analyze them, storm relative velocity can help in this regard. Base velocity is more effective in identifying straight-line wind gusts, including downbursts, particularly at the lowest elevation angle.
Join our storm chasing community. Discord link in bio.